We can represent a queue using linear arrays. Each queue has two variables, front and rear, which indicate position for insertion and deletion. Initially, both front and rear are set to -1, indicating an empty queue. The array representation of queue containing 5 elements along with the corresponding values front and rear is illustrated here. The figure displays a queue characters forming the English word smile. Since no deletion has occurred in the queue yet, the value of the front remains -1. However, the value of the rear increases by 1 each time an insertion is performed in the queue. After inserting an element in the queue will appear like this. The value of the rear will become 5, while the value of the front remains the same. After deleting an element, the value of front will increase from -1 to 0. However, the queue will appear like this. Next, we will see an algorithm to insert an element in a queue. First, we will check if the queue is full. If the queue is full, return an overflow error. If the queue is not full, increment the rear pointer. Insert the new element at the rear position. So here is an algorithm. First, check if the queue is full. If the queue is full, return an overflow error. Check if the queue is empty. If the queue is empty, set both front and rear to 0. Else, increment the rear pointer and insert the new element at the rear position. Now let us see a C function to insert an element in the queue. First, check if the queue is full. If the queue is full, print overflow. Else, check if the queue is empty. If the queue is empty, set both front and rear to 0. If the queue is neither full nor empty, increment the rear pointer. Insert the new element at the position rear. Now we will see an algorithm to delete an element from the queue. First, check if the queue is empty. If the queue is empty, return an underflow error. Retrieve the element at the front of the queue. Increment the front pointer. If the front becomes equal to the rear, set both front and rear to -1 to indicate an empty queue. Now let us write a C function to delete an element from the queue. Variable to store the deleted element. Check if the queue is empty. If the queue is empty, print underflow, else store the element to be deleted. If there is only one element in the queue, set both front and rear to -1, indicate an empty queue. Else increment front to point to the next element and return the deleted element. Now let us write a C program to implement a queue using array. This line includes input-output header file stdio.h. It provides functions like printf and scanf for input and output operations. This line includes standard library header file stdlib.h. It provides functions like malloc, free, and exit. This line defines a macro max size with value 100. Macros are replaced by their values during the pre-processing stage of compilation. So whenever the compiler sees the max size, it will replace it with 100. Structure to represent a queue. This is an array of integers used to store the elements of the queue. Max size is a macro defined earlier and it determines the maximum capacity of the queue. It is an integer variable that holds the index of the front element in the queue. This is an integer variable that holds the index of the rear element in the queue. Function to create a new queue. This line allocates memory dynamically for a new queue structure using malloc function. The size of struct queue ensures enough memory is allocated for a queue structure. These lines initialize the front and rear indices of the queue to -1, indicating that the queue is empty. Finally, the function returns a pointer to the newly created queue. Function to check if the queue is empty. This condition checks if the rear index of the queue is -1, which indicates that the queue is empty. If the queue is empty, the function returns 1, indicating true, or S. If the queue is not empty, the function returns 0, indicating false, or no. Function to check if the queue is full. This condition checks if the rear index of the queue is equal to max size -1, which indicates that the queue is full. If the queue is full, the function returns 1, indicating true, or yes. If the queue is not full, the function returns 0, indicating false, or no. Function to add an element to the queue. This function checks if the queue is full. If the queue is full, a message is printed, and the function returns without performing any further operations. If the queue is not full, the function checks if the queue was empty before adding a new element. If it was, it sets the front index to 0. It then increments the rear index to move to the next available position in the queue and adds the new element to that position. Finally, it prints a message indicating that the value has been added to the queue. Function to remove an element from the queue. This function checks if the queue is empty. If the queue is empty, a message is printed and -1 is returned to indicate an empty queue. If the queue is not empty, the function dequeues the element at the front of the queue and stores it in the variable item. It then increments the front index to remove the element from the queue. It after dequeuing the queue becomes the empty and front and rear indices are reset to -1. Finally, it returns dequeued item. Function to display the queue. This function checks if the queue is empty. If the queue is empty, a message is printed and the function returns without displaying any elements. If the queue is not empty, the function prints a message indicating that the queue elements will be displayed. It then iterates through the elements of the queue from front to rear and prints each element. Now let us write the main function of this program. Here the create queue function creates a new queue and queue 10, 20, 30 and 40. These lines adds elements 10, 20, 30 and 40 to the queue respectively, and it displays the elements of the queue. This removes and returns the front elements of the queue 10 and 20 respectively. This displays the elements of the queue after dequeuing. The output of the program would be like this. First the elements 10, 20, 30 and 40 are inserted. Then queue elements are displayed respectively, and then 10 and 20 elements are dequeued, that is deleted from the queue. So the remaining queues are 30 and 40. So this was all about the array representation of the queue and implementation of the queue using arrays. Next I will see the some of the drawbacks using the array representation. While implementing a queue using an array is straightforward, but there are some drawbacks to this approach. The first drawback is fixed size. In the array representation, the size of the queue is fixed at the time of creation. Once the queue is created with a specific size, it cannot be resized dynamically. If the queue becomes full, it is not possible to add more elements to it. Wastage of memory. If the size of the array is declared to be very large to accommodate potential maximum elements, but the actual number of elements in the queue is much smaller, it leads to wastage of memory. In the array implementation, it's possible to face two types of errors: queue overflow and queue underflow. If you try to add an element to full queue, it leads to a queue overflow. If you try to remove an element from the empty queue, it leads to a queue underflow. Continuously shifting elements. In a queue, once an element is dequeued, the remaining elements need to be shifted to fill the vacant position. This shifting operation is time consuming and makes the dequeue operation less efficient. Dynamic memory management overhead. If dynamic memory allocation is used to create an array based queue, there is a overhead associated with the memory allocation and deallocation. Array representation of queue is not suitable for real-time application where the size of the queue is not known in advance or may vary during the program execution. These drawbacks make the array representation of queue less efficient for dynamic and large-scale applications. To overcome these drawbacks, linked list representation of queue can be used, where memory utilization is more efficient and the size of the queue can be dynamic.